Welcome to the Logistics Officer Association Professional Development Module 1, Aging Weapon Systems. This module was developed by the Barksdale Air Force Base Cajun Chapter. The purpose of this module is to provide you a better understanding of the impact of aging weapon systems on combat readiness, the value of sustainment and our workforce, a primer on various sources of supply, and finally, innovation as it relates to process improvement and cost reduction. It's not often that we think of our aircraft in terms of their contemporaries, the vehicles that we drive on a daily basis, or rather, the vehicles that our grandparents drove on a daily basis. This comparison serves to illustrate what kind of challenges today's logisticians sustaining these weapon systems have to face. Many of the vehicles you see here are no longer regularly driven because of the costs associated with repairs are too high. The companies that produce them and many of their components have since been dissolved, restructured, or integrated into other corporations, making basic parts availability all but impossible and often requiring new manufactured custom pieces to remain roadworthy. What this comparison does not show, however, is the tremendous difference in the expectations levied against the respective systems. While these cars are showpieces periodically trotted out on the weekend, these aircraft are staples of our national security which absolutely must be mission capable and ready to operate at a moment's notice. It's not just the aircraft that are getting older. Our ICBM fleet of Minuteman III missiles was first deployed during the Nixon administration. Our AGM-86B air-launched cruise missiles are already 30 years old, and we are currently working on securing sufficient funds to extend that life through 2030. Security Forces emergency response vehicles programmed for replacement every 4 years are now frequently well beyond that and approaching end of life on their powertrain components. Everything from tow trucks to aircraft communications equipment is facing challenges associated with the trade-offs of affordability, effectiveness, and availability. These challenges are the subject of this module. In the Air Force, combat readiness is essential to ensuring that we are ready at a moment's notice. A high level of readiness only occurs with an aircraft fleet that is continuously able to execute its mission. Unfortunately, as our aircraft age, we face ever-evolving sustainment challenges that demand creative solutions. Our Air Force leaders are always faced with the question of whether to build a new aircraft or sustain the current fleet. With increasing budget constraints and the rising cost to build new aircraft, sustainment tends to be the popular choice. Sustainment, however, does not come without its own set of challenges. Today, we will look at the challenges aging fleets face, weapon system sustainment, and the workforce that makes it all happen. Additionally, we will cover various sources of supply, as well as innovation as it relates to finding ways to do what we do better. Let's begin with a snapshot of the Air Force aircraft inventory. As our aircraft fleet has increased in age, so has the cost associated with the operation of these weapon systems. This holds true across every Mission Design Series, or MDS. Many of our current weapon systems are within 15 years of their projected retirement, forcing the Air Force to attempt to allocate current and future year funding to recapitalization efforts despite the competing growing costs of sustaining our current systems. If the average ages you see here seem low to you, it's because the relatively high numbers of F-16 and F-15 aircraft in some ways compensate for the much older cargo and bomber fleets. Even while we recapitalize, the Air Force is increasingly relying on defense business partners to push development and unit purchase costs down. At the same time, they are being expected to make weapon systems that consider the realities of future year budget constraints. Procurement in limited role aircraft is expected to decrease dramatically, while weapon systems that demonstrate capabilities in multiple roles must increasingly receive the preponderance of the development and procurement budgets. It is the realities of this life cycle cost calculus that have led to the cancellation of the C-27J program in favor of continuing C-130 aircraft support. Innovative solutions like the multinational collaborative F-35 and its international cost-sharing program have helped to spread budget uncertainty over multiple services and international partners, making the per-unit costs effectively much lower despite cost overruns and delays in the program. Neither acquisition nor sustainment can ignore the realities of cost constraints. Now that we have an overview of the fleet, let's look at the challenges facing the Air Force today in 2013. There are many challenges the Air Force faces within the sustainment enterprise. The most prevalent include the following: a lack of metrics for field maintenance and depot activities that measure efficiency, supply chains that are inefficient due to the inability to accurately predict parts needs, increasing software maintenance requirements, which include the amount of code in systems and the complexity of the integration, the need for new technologies ready for implementation at Air Force Materiel Command's air logistics complexes, and lastly, the difference between commercial maintenance practices and military maintenance practices. The sustainment enterprise metrics currently used to measure success in terms of aircraft availability and mission capable rates are set by the lead MAJCOMs without regard for the funding required to meet the targets. The sustainment enterprise therefore consistently falls short of the targets whenever funding falls short of the requirements. There needs to be a different metric for the sustainment community that allows them to know how efficiently they are performing rather than if they are meeting prescribed MAJCOM targets. As the aircraft age, the supply system becomes more inefficient because the demand for non-forecasted parts increases and the original parts suppliers go out of business. Commercial off-the-shelf equipment causes issues because they become obsolete faster than military program life cycles require. As an example, the MQ-9 Reaper, which is still in production, suffers from component obsolescence. Software is becoming increasingly more complex due to integration with subsystems and the push towards software operation throughout the entire aircraft. The increased complexity will also require a more knowledgeable workforce in the software maintenance organizations. It is vital that this experienced core of people and technology base is built at the ALCs in order to facilitate growth. There is also a difference between commercial and military maintenance practices. Commercial airline companies maintain aircraft at flight-capable rates exceeding 90% versus 65 to 70% seen in large transportation aircraft in the Air Force. Commercial airlines do as much repair and maintenance in the field as possible and minimize depot maintenance. They document the predicted depot maintenance so they know what parts are required before the aircraft ever hits the tarmac at the depot. Forecasting allows commercial airlines to run aircraft through the depot in 30 to 45 days versus the Air Force's average of 180 to 280 days and schedules them so they are nose to tail, meaning an output occurs simultaneously as an induction is happening. Commercial airline companies have as few aircraft on the ground at the depot as possible because aircraft on the ground do not make money. Lastly, there should be more focus given to the younger integrity programs like Mechanical Systems Integrity Program, Avionics Integrity Program, and Computer Systems and Software Integrity Program to ensure they provide the valuable data that the mature programs like Aircraft Structural Integrity Program and Propulsion Systems Integrity Program currently do. The MECSIP, AVIP, and CSIP programs are just as valuable to airworthiness and fleet viability as the ASIP and PSIP programs, which have drastically reduced aircraft failures caused by structural and engine issues over the past half-century. But these other programs are far less mature and haven't yet provided the data, tools, and processes required to ensure the integrity of the Air Force's aging fleet. Now that we have an idea of the challenges that we face, let's look at the KC-135 sustainment program as an example. The Air Force is able to extend the life of its aircraft through extensive sustainment programs that we employ to provide upgrades which maintain the aircraft's relevancy, enhance or replace legacy systems, and prevent structural failures. One example of these sustainment efforts is the KC-135. Remanufacturing has enabled the aircraft to be sustained indefinitely. But what is the true value of sustainment? The average age of our Air Force fleet may be a surprise to some in the Air Force, but not to many in the logistics domain. The average age of our current fleet is 26 years old, with some airframes over 40 years old. Under current plans, these airframes will be 70 to 80 years old before they retire. As the price of the next generation fleet rises while the Air Force encounters consistent budget uncertainty, the interest in sustaining our current fleet has strengthened. There are many advantages to sustainment as opposed to new procurement outside of the obvious budgetary reasons. For starters, the reliability of older aircraft is often well known. We can predict the outcome of many events using an array of combinations between aircraft, weapons, and the environment. We know what the weapon systems are capable of doing, what the limitations are, and what commitment of manpower will be needed to maintain and generate these aircraft. Older aircraft also benefit from highly experienced personnel who track, develop, and maintain the airframes. This experience affords members the ability to troubleshoot unique differences due to their detailed knowledge of the systems and subsystems. There is also a large benefit gained from the members well versed in plans, scheduling, analysis, and testing of the older airframes. Finally, these members and systems are highly rehearsed with reviews and analysis of information gained by the decades of data collected. The trends in data have allowed for the establishment of anticipated life cycles for parts, support equipment, and primary weapon systems. Let's take a look at how procurement compares to sustainment of a new airframe. To determine the true value of sustainment, our Air Force planners must evaluate the cost of procurement. To procure a new aircraft, at a minimum, the following costs must be taken into consideration: technology development, technical order development, proprietary source data, new or modified support equipment, maintenance manpower and training, operator manpower and training, engineering support, and of course, sustainment support. Lifecycle costs from cradle to grave are tremendous. The cost of each airframe is strictly the price the manufacturer will charge per aircraft. Other costs are not typically included in this value. As a new aircraft comes online, the engineering technical data will need to be converted into Air Force technical orders. As we have seen with the F-35, there is a high likelihood of weapon system alterations to suit the dynamic conflict environment. These changes increase cost and also expose fleets to grounding, impounding equipment, or extending the time it takes to establish initial or full operational capability. In many cases, the manpower and hours needed to maintain new aircraft are drastically reduced by the development of new computerized technology, such as the case with the F-35's Alice system. These new systems can isolate faults and reduce troubleshooting time of discrepancies. These systems are expected to reduce the time it takes aircraft maintainers to troubleshoot and isolate issues discovered upon return of an aircraft or during inspections prior to the next launch. There is, however, a higher demand for items such as system inspections and time compliance tech orders, as the computerized systems are more critical to the aircraft function as a whole. There is further potential for the development of new technical schools to train maintainers on new computerized systems. This provides two further areas of inquiry. New maintenance personnel may need higher education to program and reprogram systems, possibly writing code, and contractors may be required to perform some maintenance functions, and there will be a substantial increase in line replaceable units, or LRUs. The cost of sustainment must consider future modification estimates to include upgrades and compatibilities across systems such as electronic communications and avionics. The cost is already sunk for tech order modifications, as well as facilities and support equipment upgrades and alterations. Over the decades, lean processes, research, and development have been established for respective weapon systems, which have increased the efficiency of programs and reduced the operations and sustainment costs. In the past, some airframes fulfilled non-flying alert status, thus reducing expected airframe flying hours in comparison to years in service. Therefore, when we see an aircraft within a given year group, the aircraft's actual flying hours may be greater or less depending on the specific mission sets that were assigned to those MDSs. In that light, weapon system sustainment is not only complicated by age, but by a host of other factors including mission, operating environment, and personnel. The value of sustainment can't be realized without the workforce that makes it all possible.
It's intimidating knowing that the life of the pilot's in your hands, but that's what we're here for.
Everything that this aircraft needs to function properly is what you're in charge of. You have to make sure that this aircraft is ready to go at a moment's notice.
What you're learning in tactical aircraft maintenance is basic upkeep of the jet. You're learning how to be a mechanic.
We start off by teaching them aircraft general.
Everything from hydraulics, flight controls, landing gear, engines, and fuel systems.
And from there we go into hands-on tasks.
It's only 30% classroom time and it's 70% hands-on.
The first day I got to touch the jet was pretty crazy. It was really exciting.
You realize that not everybody gets to do this.
You can always tell they get excited when we go into the blocks of training, which involve getting into the cockpit and being able to apply power, and then later on into landing gear systems when they get to swing the landing gear and do operational checks like that.
My friends back home, they're still stuck doing the same things they were doing when I was there. And I'm working on a $16 million jet, learning about ejection seats and rockets and missiles.
It is a lot of fun, and it's definitely something that you can tell they're excited about.
Before I came in, I never worked on cars or anything, and it just amazed me how quickly I was able to pick it up and fall in love with it.
A student coming out of tech school probably only has about a 1-month turnaround before he'll be on the aircraft, maintaining it and inspecting it.
I can do so many things with this career. I can go to college afterwards, try to become an officer. I can just stay in it and work on the jets for the next 20 years. I can switch and work on commercial aircraft in the civilian world. Just a lot of different opportunities and benefits that come along with being here.
As you learn how to work on the aircraft, know what to look for, and earn more responsibility, you will become a dedicated crew chief. And at that point, you will have your name actually printed on the aircraft.
In computer-age operations, maintaining and supporting weapon systems that are developed prior to the prevalence of computers creates interesting challenges. Placing a square circuit card into a round hole that used to house vacuum tubes and transistors about sums it up. Experience is the only bridge between the two, as it fills the gaps where tech data and checklists leaves open statements or schematics have changed through multiple upgrades or time-compliance tech orders. As always, the mission gets done through the know-how and can-do attitude of experienced airmen, NCOs, civilians, and engineering and test personnel. To deal with a lack of experience in maintenance career fields, the chiefs of the Air Force brought back the AFSC Shreds. Shreds identify personnel with specified skills, such as those working within a certain set of airframes like fighters, heavies, or rotary-type aircraft in order to quickly harness, focus, and redirect experience to meet mission needs on a short notice. The Air Force has continuously focused on the effectiveness of such measures. This is demonstrated through the current implementation of the new Heavy Bomber AFSC Shreds, which have helped replenish the pool of B-52 experience. For such a program to be effective, however, logistics officers must ensure record scrubs are accomplished to see that SCIs, or Special Experience Identifiers, and AFSC Shreds are appropriately awarded and accurately reflected. The workforce makes the mission happen and keeps our aging fleet airborne, but not without supply. The Defense Logistics Agency, DLA, uses demand data to determine the number of assets it stocks. They look for 2-year history at the local level. If a part has not been ordered for 2 years, DLA will pull the assets into a central hub. After 5 years of no demand history, assets are then sold as surplus on the applicable market. Several companies specialize in buying this surplus for later resale. These companies gamble that even though this asset has not been ordered in 5 years, it will eventually break and need to be ordered again. They will charge a premium for these assets when it is sold back as a way to recoup the cost of storing it in their warehouses. Depending on the part, it is not uncommon for the Air Force to pay 200 to 500% over the original cost to buy assets back from surplus vendors. Assets purchased from surplus typically will need to be inspected and tested before they are used on an aircraft. With older aircraft, this model is not always capable of accurately identifying trends. For example, with the B-52H, a 5-year history only represents 9% of its entire lifespan. While this model catches most high-demand parts, many one-off issues have been exposed, and if there is no spare part available, the Air Force may have to resort to new manufacture of the asset. It should be realized that demand data from the use of over 1,500 aircraft is more reliable than demand data from 50. Due to the number of F-16 flight hours and sorties, for example, we are given a fairly accurate picture of parts demand in a 5-year period. The B-2 fleet, on the other hand, flies far fewer hours and sorties, and it's entirely possible that in 5 years there is low to zero demand data available for certain parts. From a wholesale logistics model, it makes no sense to stockpile parts which have no demand. Storage costs money, and if there is no demand, the parts are moved out. The impact to a unit is directly felt when it takes longer to fill a MICAP. The largest contributing factor to supply lines drying up comes from the completion of initial manufacture. Typically, if a company does not think they will receive more orders for a part, they will place the tooling in storage. If they continue to go without orders, they may even destroy the tooling that was used to produce the parts. At this point, the Air Force is left with using the parts it has left in its inventory. For aging aircraft, one of the largest concerns is electronic systems. This is where the Air Force Do-In for Maintenance or DIFM program is critical to maintain. By repairing the old asset, the Air Force is able to eliminate the cost of brand new part design and manufacture. For some aircraft fleets, such as the older KC-135 and B-52H models, the original part manufacturer is no longer in business, and repairing of existing parts is the cheapest option. On the other hand, this process takes time, and it is not uncommon to see estimated repair times to last 6 months or longer. This is where the DIFM program is once again critical in reducing the time it takes to get the part to the point of repair. Supply lines for vehicle spare parts is also of concern. Going back to the economies of scale, the use of commercial vehicles means that even if it's a 10-year-old bobtail, replacement parts may be available as vehicle chassis and engines are typically produced by the hundreds of thousands. On the other hand, by the time a vehicle is 20 to 25 years old, it can be very hard to find any original equipment, or OE, parts available. This can present a challenge since vehicles should be maintained as close to OE as possible. The good news is that the private automobile industry is such that many of these old truck chassis and engines are still supported by either the original manufacturer or by someone who has purchased the original tooling and continues producing spare parts. As demand for these items dwindle, just like in the antique vehicles you saw in the beginning of this module, parts become substantially more expensive. The Aircraft Maintenance and Regeneration Group, or AMARG, is one of the most cost-effective organizations in government. For every dollar spent on AMARG's mission, $11 is returned to the applicable service. However, AMARG is a single-use resource and stock is not replenished in any way other than the addition of new, retired aircraft. There are also challenges with corrosion on older parts, and it is not uncommon to receive unserviceable parts from AMARG. Due to the process of an AMARG request, it can take 2 weeks for a pull to be approved, and from there it can take another few weeks for that same pull to be accomplished. This is due to manning limitations on the group, and while they do try and prioritize pulls, every pull from AMARG is generally of high or critical priority, so there is still a work backlog for these requests. In addition to supply, the Air Force also relies on innovation to meet sustainment challenges. Using the AFTO-22 process, personnel at all levels can identify areas in technical orders where processes can be streamlined. Coupled with the IDEA program, this is a powerful tool to continuously improve the methods and procedures used to maintain and sustain the fleet. Often, repairs can be made which keep weapon systems operating at home station. Whenever possible, these organic capabilities can be utilized in lieu of depot repair. If only partial local capability exists, the weapon system can be repaired to a mission-capable condition awaiting the complete replacement from a depot. As a CSAF-approved initiative led by HAF and Headquarters AFMC, Repair Network Integration, or RNI, is creating an enterprise repair network that allows the Air Force to optimize these resources to meet the Air Force mission.
The Air Force has taken a bold step to reinvigorate the way it conducts maintenance, repair, and overhaul with its Repair Network Integration Initiative. RNI will assist the Air Force in gaining both effectiveness and efficiency throughout the repair enterprise. RNI will better enable the Air Force to deliver the right support to the right organization at the right time, all in support of the warfighter.
RNI is going to take that global view and make sure that we have an efficient and effective organizational construct that can supply parts the most effective way by the most efficient means.
The first real test for RNI was when the tsunami struck Japan in March 2011.
This is a mandatory accountability recall for all family members and active duty members. There's a tsunami warning of 6 meters.
Many electrical generators were made inoperable, and nearly 4.4 million households in northeastern Japan were left without electricity. The loss of power combined with the transportation routes that were negatively affected, directly impacted the Air Force, putting mission performance at a serious risk.
We are the centralized repair facility for F-110 engines in the Pacific. So when the earthquake and tsunami hit, the earthquake knocked out power, which was a concern initially. We were on backup generator power, and we had everything that we needed to continue producing engines. The problem was getting those engines to where they needed to be, or getting unserviceable engines and parts in here so we could do the repairs.
By redirecting engines, we moved 9 engines retrograde back to the United States, to repair locations in the United States, and spares from the United States over to Korea.
In the past, what would have happened is we would have had our tsunami. Everybody would have been aware that this giant earthquake and tsunami happened, and maybe that there had been some impact on Misawa, but nobody would have asked about our engine production capability until we couldn't fly an airplane, and so we were able to do that proactively because of R&I.
And if we don't figure out how to connect into the repair network when it comes to any component, then we're missing the boat. So as long as you have a viable, responsive transportation system, transportation network, then R&I works very effectively. It's too expensive in our Air Force to have decentralized everything. R&I is not if, it's when.
I think R&I, the biggest benefit is the airmen on the flight line, or more importantly for engines, the shop chief and the airmen in the JIM shop, the intermediate shop, to let them know, hey, if you need a part, if you need an engine to make sure you can meet your spare requirements, the network's going to provide that to you. And we have demonstrated performance we can do that. I think the biggest proof point is on the F-100-229. When we implemented R&I, we were at less than 10 war readiness engines or spare engines for the 229 fleet versus a requirement of 39. Today we're at 38 or 39 engines on a regular basis. We haven't added any more engines to the system. We haven't increased the number of people working on the engines. We've just managed the network more effectively so we can move the parts we need around the network to produce the maximum number of engines on a given day, a given week, or a given month.
There's a clear case for change, a clear case for assessing our business model and how we operate. And so I think there's a compelling case for General Feder and a compelling case for the rest of us who are involved specifically with R&I.
R&I is a must-have concept, so matching up our logistics priorities to our Air Force priorities is clearly the right thing to do.
I like stretch goals, and I think as we tackle this under the new 5-center construct with AFSC, LCMC, working in concert with the A4 community, I think it's doable. There are certainly challenges associated with all the various areas for achieving the R&I objectives, but it's certainly one that's worth striving towards.
R&I is key to our ability to provide future support to the warfighter. It is fundamentally improving repair processes so airmen are better equipped to do their job, resulting in more mission readiness at less cost for our Air Force.
Many components of various weapon systems can be repaired locally per tech data. By diligent adherence to the established processes, parts can be fixed in back shops or depots rather than being replaced by the manufacturer. This allows the Air Force to reap tremendous savings by continuing to use parts already owned and paid for. Successful repair enhancement initiatives save the Air Force time and resources by using organic capability over the different process for parts that would otherwise require higher level repair and greater time awaiting parts. The Air Force Repair Enhancement Program, or AFREP, is quantified by cost avoidance and cost savings, and once a successful AFREP initiative is identified, it can be repeated to further generate and enhance combat capability. Cost avoidance is the repair of items to avoid replacement costs. The program repairs items such as circuit cards, aircraft parts, printers, shredders, and televisions for base organizations. It is limited to repair items based on funds, warranties, and authorizations. Cost avoidance also encompasses aircraft assets that can be repaired on base, but are not ordered enough to warrant or have the item added to the cost savings repair list. Cost savings are either aircraft or aircraft support equipment assets that can be repaired for less than 50% of the cost of a new like item. For cost savings, AFREP is limited to repair items that are coded as either expendable or base repairable items. Innovation is critical to the sustainment of our aging fleet. In this professional development module, we learn that the Air Force faces significant challenges with its aging aircraft, none more important than the intense demand on the supply system and the continuous need for repairs and upgrades. We saw the value of sustainment and compared it to the process and cost of procurement, and also discussed several sources of supply which highlighted many of the options that are available to meet the demands of our aging fleet. Without our dedicated workforce, which brings a tremendous amount of experience, innovative ideas in the form of process improvements and cost savings initiatives such as repair network integration, our aging fleet would not be the superior Air Force that it is today.